Hi everyone. Notes 2.6 are on factoring special patterns. And just like we've done with every other set of notes, we're going to do the multiplication first so that way we can see so that way we can understand what's going on because with factoring, we're just undoing the multiplication. So in this first example here, we need to multiply the following binomials together. You can use whatever method you like to do this. So you can FOIL, you can just use the distributive property. Those are pretty much the same thing. You can use the box. It doesn't matter. I'm just going to FOIL just because it's quick and I just want to get through this quickly. So F stands for first. So I'm going to multiply the firsts together. X times X is X squared. Then I'm going to do the outside or the outer. X times 4 is positive 4X. Negative 4 times x is next, which is negative 4x, and then negative 4 times 4 is last, which is negative 16. The 4x and the minus 4x cancel each other out when I collect like terms, so I just get x squared minus 16 here. Okay. The next example, let's go ahead and do this one using FOIL as well. So 3x times 3x, 3 times 3 is 9. I get 9x squared. X times x is x squared. 3x times negative 5 is negative 15x. Positive 5 times 3x is positive 15x. And then 5 times negative 5 is negative 25. Again, the minus 15x, the positive 15x, they cancel each other out. So I end up with 9x squared minus 25. So if you notice, what ends up happening here is the outer and the inner terms cancel each other out in both of these. And the reason why is because the outer that we have right here is a positive 4x, and the inner that we have here is a negative 4x. So they cancel each other out. But the biggest reason why is because these expressions are identical except for this minus sign here and this plus sign here. And same thing is true in this example here. So this 3x and negative 5, and then this 3x and positive 5 cancel each other out again because they are identical except for the plus and the minus. As opposed to something like this where we would have like x plus 7 times x minus 4. The outer and the inner don't cancel each other out because they're not identical except for the sign. So this is called a difference of perfect squares, and the general form for a difference of perfect squares is a plus b times a minus b, and you end up getting a squared minus b squared. And the reason why is because when you do your first, you get a squared. When you do your outer, you get negative ab. When you do your inner, you get positive ab. Those two cancel out. When you do your last, you get negative b squared. So this time, when we are doing our factoring here, we are going to look and see how to identify that it's going to be something like this. And this is called a difference of perfect squares. So here are the 3 requirements for a difference of perfect squares. First of all, you have to have a binomial. You have to have 2 terms. Why do you have to have 2 terms? Because typically we end up getting 4 terms when we FOIL. We always get 4 terms when we FOIL, but the outer and the inner cancel each other out, so we're left over with 2 different terms. The second requirement is you have to have subtraction. And the reason why you need subtraction, first of all, that's where the word difference comes from. The reason why you need to have subtraction is because the only way that the outer and the inner cancel is if the signs are opposite of each other. But if they're opposite of each other, then these have to be opposite, and the negative times the positive gives us this negative that we have right here for this 16. And then the last requirement is that we have to have perfect squares. If all 3 of these things are in the expression, then we know it's a difference of perfect squares, and differences of perfect squares are one of the easiest factoring problems you could get. So let's take a look at question number 3. In number 3, we've got x squared minus 9. So let's look at our requirements. Is it a binomial? Absolutely, it's 2 terms. Is there subtraction? Absolutely, there's a subtraction sign right here. Do we have perfect squares? Yes, we do, because the square root of x squared is x, and the square root of 9 is 3. So we know that these are perfect squares. Let's factor this though, like we normally would factor any expression at all. So right here, this is the first and this is the last. And the outside and the inside would cancel each other out. So since the first right here would be x squared, I need this times this would be x times x would have to give me x squared. Since the last is negative 9, let's just deal with the 9 first. We would have a 3 and a 3, or we could try 9 and 1. But in order for our outside and our inside to cancel out, they have to match, except one has to be positive and then the other one has to be negative, which is exactly what we have here, which means that this 3 right here is positive and then this 3 right here is negative. So you can see here, you're pretty much doing the exact same the exact same factoring that we've done before. It just happens to be a special case where the outside and the inside cancel each other out. Now, if you can recognize that this is a difference of perfect squares though, the factoring can just be super easy. You just take the square root of the first term right here, which is x. You take the square root of the second term right here, which is 3, and then you can just put a plus and a minus sign. So that's why I was saying this is some of the easiest factoring that you can do. Okay, so in number 4 right here, in order for this to be a difference of perfect squares, it needs to be a binomial, which it is. It's 2 terms. But then you have to have subtraction, which we don't have here technically because there's a positive sign here. However, I can rewrite this with the x squared first and the minus 25 last, and now it does have subtraction, so it does satisfy that requirement, and these are both perfect squares. So I can just factor this as a difference of perfect squares. The square root of x squared is x, so I'll put x in the front, x in the back here. The square root of 25 is 5, so I'll put a 5 here and a 5 here. And then I would need to have opposite signs. Now, it does not matter if you put the plus sign first or if you put the minus sign first. It doesn't matter. It's the exact same thing. So let's double check to make sure that this is going to work for us. So here, the outside is x times 5x, which is 5x. The inside is negative 5 times x, which is negative 5x. They will cancel each other out. X times x is x squared. Negative 5 times positive 5 is negative 25. So this definitely for sure will work out for us. Right, and number 5, I need to look and see if this will satisfy my 3 conditions, this x squared plus 49. So is it a binomial? Yes, it is. It does not have subtraction, even though I have perfect squares, because it doesn't have subtraction, this is not a difference of perfect squares. This is not possible. And let me show you why this is not going to be possible. So like right here, the first would be x times x would give me x squared. The last would be 7 times 7 gives me 49. When I do my outer here, I get 7x. When I do my inner here, I get 7x. And since the x's clearly cancel out right here, that means that one would have to be positive, the other one would have to be negative, which means that this would have to be a plus sign, this would have to be a minus sign, which means that the 49 would be a negative 49. So this is not possible with these values here. So let's get this to become a positive 49. So instead, I'll just use a plus sign here and a plus sign here. But the issue with that is that the 7x and the 7x no longer cancel out. And this would actually be x squared plus 14x plus 49. So that doesn't work. Well, what if I change this to a minus times a minus right here, which would turn the outside and the inside into subtraction, which would still not cancel. So this is not possible at all. So what we do is we say here it's not factorable. And because it's not factorable, we also will just say that it is a prime expression. All right, our last example on this page is x to the power of 4 minus 16. It is a binomial. There are 2 terms. there is subtraction, and I have perfect squares. So the square root of x to the power of 4 is x squared. The square root of 16 is 4. So I definitely can factor this as a difference of perfect squares. So I'll put x squared and x squared first, 4 and 4 last. One of them is plus, one of them is minus. And typically we'll box this and we'll say, oh, we are done. But in fact, we actually are not done, because this x squared minus 4 right here has two terms, has subtraction, and has two perfect squares right here. Perfect square, perfect square. So I can actually factor this expression that we have here even further. So the square root of x squared is x. The square root of 4 is 2. And then I can put a plus sign and a minus sign. Well, what do I do with this? I just copy this down. Why didn't I factor this any further? Because this is not a difference of perfect squares. So this right here would end up being my final answer. So that wraps up our discussion of differences of perfect squares. There's another special pattern that I would like to talk about here. So turning to the next page, in number 7, this is exactly the same or almost exactly the same, except instead of having a plus and a minus, the two signs actually match. So when I FOIL this, x times x is x squared. When I do my outer, I get negative 4x. When I do my inner, I get another negative 4x, which does not cancel out. And then negative 4 times negative 4 is positive 16. So now these actually get put together. You get x squared minus 8x plus 16. And so this is what it's going to look like right here. This is my final answer for this one. And just like in number 2 before that we had done on the previous page, we had a plus and a minus here. This time we have two pluses. So let's go ahead and FOIL this. So 3x times 3x is 9x squared. 3x times 5 is a positive 15x. 5 times 3x is another positive 15x. And then 5 times 5 is positive 25. So again, these do not cancel out. You can actually put them together. So you get 9x squared plus 30x plus 25. Form for a perfect square trinomial. So how is this a perfect square trinomial? Well, if you notice right here, the result is a trinomial, but the thing that you are actually foiling together is this x minus 4 times x minus 4. That's what you're expanding. That's what you're multiplying. So if you notice, this pretty much is just saying x minus 4 squared. And when I square it, I get this perfect square trinomial. And same thing with this one over here. You have 9x squared plus 30x plus 25. This is a perfect square trinomial because it is the trinomial result of 3x plus 5 being squared. Okay, so the general form is going to be a plus b times a plus b is equal to a squared plus 2ab plus b squared. Where do we get that from? Just by foiling it or expanding it or multiplying it or distributing it, whatever you prefer. So a times a is a squared, a times b is ab, b times a is ba, but we can also call it ab, and then b times b is b squared. And 1ab plus 1ab gives me this 2ab. Because they're identical, these middle terms here, there's gonna be double what you get when you do the outer or what you get when you do the inner. So if you notice here, the a is the x, the b is the negative 4. So if I follow this format right here, a squared is x squared, 2ab is 2 times x times negative 4, which is negative 8x, which is what we have here. And then the b squared is the negative 4 squared, which is 16. Okay, and the same thing is true right here. To be completely honest, when we do these factoring questions here, typically we just do it like we would factor any other trinomial, to be completely honest. So like, for example, right here, if I were to look at this and I don't recognize that it's a perfect square trinomial, I would still see that the first two terms have to multiply together to give me x squared. So those choices are x and x. And that the last terms have to multiply together to give me 9. So I could use 1 and 9 or 3 and 3. Let's try 3 and 3. So then my outside right here would give me 3x. My inside right here would give me 3x. If they're both positive, then I would get a positive 6x, which is exactly what I'm looking for right here. So I could just say here that this is my answer, or I could also just say x plus 3 quantity squared. Now you could also recognize that this is in the format a squared plus 2ab plus b squared. And I can see based on this that if a squared is x squared, that's what this is saying right here, then a has to be x. And if b squared is 9, then b would have to be 3. Just to double check what this 2ab is right here, I would do 2 times a, which is x, times b, which is 3, which would give us the 6x that we have right here. So right here, if I recognize that this is a perfect square trinomial, then I can say here that a squared is 25x squared. Well, if a squared is 25x squared, then a is the square root of this. So 5 times 5 is 25, x times x is x squared. And I also know that b squared has to be this 36y squared that we have here. So square root it, the square root of 36 is 6, the square root of y squared is y. So then my middle term right here would have to be 2ab. So I would do 2 times a, which is 5x, times b, which is 6y. So 2 times 5 times 6 is 60, and then x times y is xy, which is exactly what we have here. So how do I apply that? How do I factor this? This just means that it would have to be the a right here in the front, the b right here in the back, and the b is positive, so this would be my answer. But again, you could just do guess and check with this until it works out for you, okay? All right, in number 11, I'm going to do guess and check for 11. So for number 11, I know that the first terms will multiply together to give me x squared. My only options are x and x. And I know that my last terms will multiply together to give me 49. And 49 is nice because I only have 1 and 49, or 7 and 7. Let's try the 7 and the 7. So my outside would give me 7x. My inside would also give me 7x. But in order to get this negative 14x, the 7x here has to be negative, the 7x here has to be negative. So this is a minus 7, this is a minus 7, and this right here is my final answer. Or you could also just say x minus 7 squared. Either one of these would work. And then in our last example, I also want to do some guess and check for this one right here. So my first terms would give me x squared when I multiply them. So this has to be x times x. And then for my last term right here, it would be 25 right here. So I would look, it would be negative 25, but I'm going to worry about the signs afterwards. So I could either try 1 and 25 or 5 and 5. I will try 5 and 5 because that seems more likely that I'll be able to get a negative 10 from it. So right here, x times 5 is 5x. That's my outer. My inner right here would also be 5x. And in order for me to get a negative 10 right here, both of these signs would have to be negative. So this right here would be a negative 5, this would be a negative 5. But if I multiply this negative 5 by this negative 5 together, I do not get a negative 25. It's not possible. The only way that I can get a negative 25 is if one of these 5s was positive. Well, if one of these 5s was positive, then this negative 5x and this 5x would cancel each other out, and this would actually be a difference of perfect squares. So one quick note is that in order for us to be able to have a perfect square trinomial, by the way, this is just not possible. In order for us to have a perfect square trinomial, this has to be a positive b squared. It has to be, no matter what. So because of that, because this is not positive, we would say that this is not factorable, or if you remember, we also say that it is prime. Now, even though these are special cases, everything that we've learned so far this unit would still apply. So if you don't want to memorize these special cases, that's totally fine. You don't have to. You'll still be able to factor it. Okay, that's it for this video. Let me know if you have any questions, and I will see you in class. Bye.